Usually, when we picture a volcanic eruption, the immediate image that comes to mind is, well, pretty apocalyptic.
Oh, absolutely. It's like nature hitting the panic button.
Right. We see it as this ultimate symbol of natural destruction. Massive pollution, millions of tons of ash, toxic gases, thick black smoke, just totally blotting out the sun.
Yeah, we instinctively categorize it as an environmental disaster. You look at an eruption and you just assume it's throwing this massive wrench into the delicate balance of our atmosphere.
Exactly. Just flooding the sky with things that simply shouldn't be there. But what if we completely flip that script?
Which is a wild concept.
It is.
Yeah.
What if one of the most violent, explosive volcanic eruptions in recent human history didn't just pollute the sky, but actually acted as a giant atmospheric air purifier?
I mean, it sounds totally counterintuitive.
Right.
It's a paradox that really forces us to rethink our basic assumptions about how the Earth's systems actually interact with one another.
And that mind-bending paradox is the exact focus of today's deep dive. We are looking at a really fascinating study that was published in Nature Communications on May 19, 2026.
Yeah, looking back at the January 2022 eruption of the Hunga Tonga volcano.
Which was just a massive event. So our mission for you today is to unpack this incredible plot twist in the scientific data. We're going to explore how this specific volcano released an immense amount of methane.
Which is a highly potent greenhouse gas, obviously.
Right, a terrible greenhouse gas.
Yeah.
But simultaneously, it triggered a bizarre chemical chain reaction that actively destroyed that very same gas.
The scientific detective work behind this study is just phenomenal. And as we break down the mechanics of it, it should fundamentally challenge how you view the hidden balancing acts of our atmosphere.
We tend to think of it as static, right?
Exactly. We often view the climate as this rigid machine. But this event reveals a dynamic, chaotic, and, self-regulating side to the planet that we are only just beginning to understand.
Well, let's start with the event itself, because the visuals alone are just staggering.
Oh, the satellite footage is insane.
It really is. So we are talking about January 15, 2022, the Hunga Tonga volcano violently detonates. And looking at the imagery, you see this colossal, almost terrifyingly beautiful plume of ash and water vapor just punching straight up through the clouds.
Rising miles and miles over the ocean.
Yeah, and threading all the way through this dark, churning gray mass are these intense, jagged forks of lightning.
The sheer force of that upward propulsion is actually the first critical piece of this whole puzzle.
Because it wasn't a normal volcano.
Right. To understand why this eruption was so unique, you have to look at where it happened. This was a submarine volcano.
So it was entirely underwater.
Exactly.
Right.
The caldera was submerged under the South Pacific Ocean. So when the eruption began, thousands of degrees of superheated magma instantly met freezing ocean water.
Which sounds like a recipe for a massive steam explosion.
That's exactly what it was. It triggered an instantaneous phase change. The water flashed into steam, expanding its volume exponentially in like a fraction of a second.
Right.
And that violent expansion acted like a geological cannon. It fired material completely past the lower atmosphere, directly up into the stratosphere.
Which is an upper layer of our atmosphere that, very rarely sees this kind of sudden, massive chemical injection.
Almost never.
And one of the things it injected was a staggering amount of gas. The data from the study put some hard numbers on this, which are wild. The eruption released roughly 300 gigagrams of methane into the atmosphere.
That is a huge amount of gas.
It is. And to put that into perspective for you, if you take the annual methane emissions, like the burps and belches, of over 2 million cows.
2 million cows?
Yeah, 2 million cows. And you suddenly release all of that gas into the sky in one single explosive moment. That is what this volcano did.
And on the surface, that looks like a devastating blow to the climate. Methane is an incredibly aggressive greenhouse gas.
But, and here is the crazy twist, the researchers found something astonishing happening inside that cloud.
Right.
While the volcano was dumping all of this methane into the air, the volcanic plume itself was simultaneously acting as a methane destroyer.
It's just wild.
The data shows the plume was eliminating nearly 900 megagrams of methane every single day.
Oh.
So you have a natural event simultaneously polluting and cleaning the atmosphere at the exact same time.
Though we should probably clarify that the overall net balance wasn't exactly in favor of the cleanup.
Fair point.
300 gigagrams of methane released is a staggering amount, and destroying 900 megagrams a day, while significant, means the volcano was still a net polluter in the end.
Right, it didn't zero itself out.
Exactly. The true discovery here is the fact that this destruction was happening at all. And at such an unprecedented scale, it exposed this completely unexpected atmospheric mechanism.
But wait, I have to push back a little here. The stratosphere is miles up, right? And the plume itself is this chaotic, opaque mess of ash and lightning.
Oh, total chaos.
So how on earth do you definitively measure an invisible gas disappearing inside of that?
Well, you don't look for the methane itself.
You don't.
No, I mean, think of it like a crime scene. When you're trying to solve a crime and the culprit has vanished, you look for the fingerprints. You look for the remains.
Okay.
The researchers knew that when methane breaks down in the atmosphere, one of the immediate byproducts of that chemical reaction is a completely different chemical.
Which is what?
Formaldehyde.
Wait, like the preservative they use in high school biology labs?
The very same. The team realized that if they could find a massive, unexplained spike in formaldehyde, exactly where the volcanic plume was traveling, they would have their smoking gun.
Oh, I see.
It would be undeniable proof that methane was actively being torn apart in that specific location.
But still, tracking formaldehyde from space seems incredibly difficult. How do you monitor trace gases on a global scale like that?
You use some of the most advanced environmental monitoring technology we have in orbit. The researchers relied on data from the Sentinel-5P satellite.
Okay, I've heard of that one.
Yeah, it carries an instrument called TROPIMI. TROPIMI acts as an incredibly sensitive atmospheric spectrometer.
So it's looking at light.
Exactly. It looks at the sunlight reflecting off the Earth's surface and bouncing back into space. Different gases absorb different specific wavelengths or, colors of that light.
Like a barcode.
Exactly like a barcode. By analyzing the barcode of the light that makes it back up to the satellite, TROPIMI can identify the chemical signatures of different gases, even in really minute amounts.
And the satellite imagery from the study is just fascinating to look at. On the map from January 16th, which is the day after the eruption, you can see the coastline of Australia.
Yep.
And stretching out over the dark blue of the ocean is this massive, striking blue cloud, perfectly tracked by the satellite. And that blue cloud represents the formaldehyde.
Right. And what TROPIMI revealed about the behavior of that cloud is what really blew the researchers away. The satellite tracked this massive mass of formaldehyde moving off the coast of Australia for 10 solid days.
Which, 10 days doesn't really sound like a long time for a cloud to drift, does it?
It doesn't, until you factor in the chemistry of formaldehyde. The lead author of the study, Martin van Herpen, pointed out this crucial detail that makes this a breakthrough.
What's the detail?
Formaldehyde is an incredibly fragile molecule. Under normal atmospheric conditions, it simply cannot survive for 10 days.
Oh, really?
Yeah, it gets broken down by sunlight and other chemical reactions in a matter of hours.
Okay, let me make sure I'm following the logic here.
Go for it.
If formaldehyde only lasts for a couple of hours before vanishing, but the satellite is clearly tracking this massive blue cloud of it for 10 straight days,
Right.
then the formaldehyde isn't just leftover gas from the initial explosion.
Exactly.
It must be actively, continuously created over and over again as the plume moves.
You hit the core of the discovery right there. The methane destruction wasn't a flash in the pan that happened the moment the volcano erupted.
It was ongoing.
It was a continuous, ongoing chemical reaction happening inside the moving plume day after day, just constantly churning out fresh formaldehyde.
Wow. But proving that continuous reaction must have been a nightmare for the data scientists, right? Especially given all the other gases volcanoes spit out.
Oh, it was an immense analytical challenge because volcanic plumes are absolutely loaded with sulfur dioxide.
Okay, and why does that matter?
The problem is that sulfur dioxide and formaldehyde absorb very similar wavelengths of ultraviolet light.
So their barcodes look alike.
Exactly. For the satellite sensors, trying to read the faint formaldehyde signal over the massive roar of sulfur dioxide is like trying to hear a whisper next to a jet engine.
So how do they filter out the jet engine to hear the whisper?
They had to uncouple the data mathematically. The researchers painstakingly analyzed the subtle differences in the absorption spectra, those tiny variations in the barcodes of the two gases.
Sounds tedious.
Very. And they applied these complex algorithms to strip away the sulfur dioxide noise, They also had to correct for the extreme altitude of the plume because temperature and pressure way up in the stratosphere alter how these gases interact with light.
So it wasn't just a simple readout.
Not at all. Only after passing the data through all those rigorous filters could they prove the formaldehyde signal was undeniably real.
Okay, so we have the crime scene, the chemical fingerprints, and the satellite footage proving it happened continuously.
We do.
But what actually triggered this? I mean, ash and seawater everywhere, so what made this specific plume act like a chemical buzzsaw?
The answer lies in that underwater explosion we talked about earlier. Because the Hunga Tonga volcano detonated beneath the ocean, it blasted an enormous mixture of volcanic ash and salty seawater straight up into the stratosphere.
Right, the geological cannon.
Exactly. When you miss those specific elements in the extreme dry, cold environment of the upper atmosphere, they form what are called iron salt aerosols.
So just like billions of microscopic, chemically loaded dust particles suspended in the air.
That's it. Now add the final ingredient to the recipe, which is the sun.
Okay.
When intense, high-altitude ultraviolet sunlight hits these suspended iron salt aerosols, it triggers a powerful photochemical reaction. The solar energy essentially bakes these particles, causing them to release free chlorine atoms into the surrounding air.
So now you just have chlorine gas floating around in the stratosphere.
Yep. And in atmospheric chemistry, a free chlorine atom is a highly aggressive, incredibly reactive radical.
Like it wants to bond with things.
Or break things. When it encounters a methane molecule, it doesn't just bump into it. The chlorine violently tears the methane apart, stripping away a hydrogen atom.
Wow.
That breaks the methane down, destroying its ability to act as a greenhouse gas entirely, and leaving behind byproducts like
formaldehyde.
Exactly.
So it's like the volcano accidentally built a giant solar-powered stratospheric washing machine. You've got the ash and the sea salt acting as the detergent, and then the sunlight turns it on, creating this chemical chlorine bleach that just scrubs the methane right out of the sky.
That is a brilliant way to visualize it. It is literally a massive chemical bleaching event. And what intrigued the scientific community even further is that this chemical mechanism isn't entirely new to science.
Wait, it isn't?
No, we just never expected to see it triggered by a volcano at this altitude.
So where else have we seen atmospheric bleaching like this?
Well, Matthew Johnson, who is a researcher from the University of Copenhagen who worked on the study, points out that we have observed this exact same chlorine-driven destruction in massive dust clouds blowing over the Sahara Desert.
Over the desert.
Yeah, the Sahara dust interacts with sea salt from the ocean and sunlight in the lower atmosphere to create the same methane scrubbing effect.
But the Sahara dust stays low, right? Like the troposphere. Whereas this volcano shot the ingredients miles higher up into the stratosphere.
Exactly. Finding this mechanism happening so high up, triggered by a submarine volcano, shows that nature has these repeating chemical motifs.
That's a cool phrase, repeating chemical motifs.
It really is. The Earth can trigger the same complex cleaning mechanisms in vastly different environments using totally different delivery systems.
Well, let's bring this fascinating chemistry down to Earth for a minute and look at the stakes for us.
Yeah.
We talk constantly about carbon dioxide when we discuss the global climate crisis. Where does methane fit into the picture, and why does scrubbing it matter so much?
Okay, think of carbon dioxide like a slow, rising flood. It builds up steadily, it lingers for centuries, and it causes long-term generational warming.
Okay, the flood and methane.
Methane, on the other hand, is like a blowtorch.
The blowtorch.
Yeah, it burns incredibly hot and fast.
Wow.
Over a 20-year period, methane is 80 times more effective at trapping heat in our atmosphere than carbon dioxide.
80 times. That is a massive multiplier.
It is. It creates a rapid, intense warming effect that drives extreme weather in the near term.
So it's much more aggressive.
Very. But its crucial weak point is its lifespan. While that CO2 flood takes centuries to recede, the methane blowtorch naturally burns itself out in about a decade before breaking down.
Ah, I see. So if you can just turn off the valve on the blowtorch, the immediate heat drops instantly.
Precisely. Reducing CO2 is non-negotiable for the long-term survival of our climate systems. We have to stop the flood.
Right.
But methane reduction acts as a climate emergency brake. Because it leaves the atmosphere so quickly, if we start adding to it, or yet figure out how to scrub it out artificially, we would see a very sudden, very tangible drop in the rate of global warming.
Which buys us time.
It buys us the time we desperately need to do the harder long-term work of decarbonizing our energy grids.
That makes this volcanic eruption much more than just a cool anomaly. I mean, it proves that scrubbing methane out of the open sky at a massive scale is physically possible.
Yes, and it also proves that we can verify it when it happens.
Verification is huge.
It is. Shasta, a scientist from the Royal Netherlands Meteorological Institute, brings up a vital point in this study regarding climate technology.
What's that?
Well, there are startups and research labs all over the world trying to build our own artificial versions of that stratospheric washing machine. They want to deploy technologies to pull greenhouse gases right out of the air.
But the biggest hurdle those startups face must be proving to governments or investors that their tech actually works.
Exactly.
Because how do you prove you've removed an invisible gas from an open, windy sky?
It's been a massive problem, but this study provides the exact blueprint they need. This volcanic event proves that our current satellite technology, like the Sentinel-5P, can directly measure massive-scale methane destruction by tracking the chemical byproducts.
It's like the formaldehyde.
Exactly. It is a monumental leap forward for verifying future climate tech. If we deploy a methane scrubbing technology tomorrow, we now know we have the orbital tools to watch it work in real time.
Just separating the genuine solutions from the snake oil?
You got it. It takes a lot of the guesswork out of climate engineering. But, this discovery also fundamentally disrupts our current understanding of the planet's baseline behavior.
How so?
It forces scientists to rewrite the rule book on the global methane cycle.
Oh, wow.
Up until this study was published, global climate models, the incredibly complex computer simulations we use to predict the future of global warming, they largely ignored the impact of atmospheric dust and volcanic ash on methane degradation.
Wait, they just didn't factor it into the simulations at all?
They didn't know the mechanism existed at this scale.
That's crazy.
The underlying assumption was that methane degradation was mostly just a steady, predictable background process. But because of this single eruption in 2022, Matthew Johnson and the research team insist that we now have to revise our global estimates entirely.
Because there are unpredictable spikes.
Exactly. We must account for the fact that every time a volcano erupts or a massive dust storm kicks up over a desert, the Earth might be triggering its own chaotic, built-in cleaning mechanisms.
And if our models are missing that?
Then if our models don't account for these sudden natural drops in methane, our predictions about the speed and severity of future warming simply won't be accurate.
Man, looking at the whole picture we've painted today, the journey is just wild. We started with a violent oceanic eruption that usually signifies disaster and pollution.
Right.
But instead we found an incredibly complex chemical ballet. You have a submarine volcano that blasts ash and sea salt miles into the sky, where the sun bakes it into a chlorine bleach that actively hunts down and destroys one of our most dangerous greenhouse gases.
It is a profound testament to the staggering complexity of the Earth's atmosphere. It demonstrates that the planet isn't just passively sitting there absorbing the pollution we generate.
It's fighting back, in a way.
Yeah, it is a reactive, dynamic system with its own built-in, albeit chaotic, mechanisms for atmospheric cleaning.
It's like the ultimate silver lining to a volcanic ash cloud. But I feel like it also leaves us in a really interesting place regarding our own ambitions to fix the climate.
It does. And actually, that brings up a fascinating philosophical question for you to ponder long after this deep dive ends.
Let's hear it.
We are currently trying to engineer our way out of a climate crisis, right? We are researching solar geoengineering, artificial carbon capture, and massive methane scrubbers.
Right, trying to take control.
But if nature's own method for scrubbing the atmosphere involves chaotic, violent volcanic explosions shooting sea salt miles into the sky to create highly reactive chlorine gas.
Uh-oh.
What does that say about our attempts to artificially replicate it? If we try to build our own atmospheric washing machines, are we truly prepared for the potentially chaotic, unforeseen side effects of tampering with a chemical system that is clearly far more complex than our best supercomputers even realize?
Wow. It really makes you wonder if our attempts to carefully turn the dials on the climate might accidentally hit the exact same chaotic panic buttons the Earth uses. The diagnostic X-ray of our atmosphere is definitely a lot murkier and honestly a lot more fascinating than we ever thought. Keep looking up. We'll catch you on the next deep dive.